Hello, everyone. Please join me in welcoming Juliet, a data scientist from Cloudera, who is also a maintainer of Sparkling Pandas.
Good afternoon. Can you all hear me all right? Good level? Not very responsive. I'm not actually going to pull you too much, but I really like a little bit of audience interaction. So I have a question. I have a few questions. Who has a right hand? Yeah. Who has a left hand? Who uses Spark? Who uses Scala Spark? Who uses PySpark? Who wants to learn how to use PySpark better? Awesome. Great. This gives me lots of good information, kind of what I expected today. So today, obviously, I'm talking about PySpark best practices. I'm a data scientist at Cloudera, and part of my job is to work with customers and to make sure that customers are successful with whatever tools that they choose. So when I go to them, they are jazzed about Spark. They want to use it. They think it's going to be a wonderful, useful API that will really let them get at huge amounts of data. When I talk to their teams, I would say in a team of 10, the manager will say, we're going to use PySpark, and 7 out of 10 will be very into that, and there's 3 that want to learn Scala. And for those, I set them up, help them all the way, but from my perspective, I'm used to using Scala Spark, at least initially when I joined Cloudera. And so I realized, seeing this pattern over and over again, the demand for Python and PySpark, that I needed to start learning and using PySpark a lot more with customers and trying to help them be as successful as possible. So usually what I do is something simple with their data to give them an example of how to use PySpark. So I was working with a retail customer where they have a huge number of stores and a huge number of items, and they want to understand on a per store item basis when there's outliers in their sales. And so the sort of examples you'll see sort of strung through this talk are based on that particular use case. Wow, I got a good view of my cough there. So all the examples you'll see are based on that particular use case. And what I'm going to talk about first is how PySpark works, how it all fits together, so I can motivate what I think best practices for PySpark are. So allow me a mild digression into explaining how Spark works and how PySpark works, and then I'll move on to best practices, which I think is what you're all here for. So, we're using Spark, we get a Spark context, and we want to do something like read in data from a file, do some processing on it. So in this case, I had a file that had keys that were store ID, item ID, and values that were the number of items sold in that day. And so I created a method that takes all of these. I guess this one I had already aggregated all the key value pairs together, maps over them, and creates a series, so a pandas series, something that Python users are used to using. Does an operation on that pandas series. I have a model that declares whether or not that series has an outlier in it, and then I count how many outliers exist. So what Spark is doing is that it reads in a file. Each of these partitions gets read in as a section of your RDD, and we have a resilient distributed data set, which is our initially read in text file. We map over it, we apply another function, filter, remove all of the non-outlier time series, and then we count them. So to begin to really get at why PySpark is different, we need to understand the general operational model of Spark, and then how Python gets attached to it. So overall, I think we're probably familiar with this diagram and have seen it over again in this conference, but one more time. So in PySpark, inside of our driver context, inside of our driver program, we get a Spark context. And that Spark context allows us to describe the operations we're going to do on RDDs. These get compiled into a DAG, which get translated into stages, which then get executed on the worker nodes. And so the worker nodes have executors in them, and each of these executors end up processing multiple tasks, which tend to correspond to partitions of RDDs. So all of the blue boxes here, I like to imagine as JVMs. This is where a lot of the work in Spark actually gets executed. So we add PySpark into the mix, and we're not writing any code in Java, and of course we're executing Python on the cluster. So how does that change things? Well, on the local side, in the driver node, we have a Python Spark context. We get the same thing, where inside of our Python script or Python class, we have a Spark context that we can create RDDs from. All of the operations that we describe as happening on those RDDs in our Python code get translated into operations on an actual Java Spark context. And so the way the communication between the Python process that's running your Python driver program and the JVM that's executing the driver part of the Spark program works is that it uses a program called Py4j. So Py4j allows you to operate on Java objects from Python. So you can say org.apache.spark.spark context, like so under the hood, org.apache.spark.spark context, and we create a new Spark context in some associated JVM. So that's happening on your sort of local driver node. On the cluster, it's a little less transparent. So what's happening is that you still have Java executors. These Java executors are still operating on tasks. And the way that the RDD is represented to the Java executors is in the most generic way possible. You have an RDD of bytes. And so somewhere along the line, we need to have to know how to translate these Python objects that we actually write our code around into bytes. So looking at my example again, I'm mapping over my RDD and applying this Python function called toSeries. And applying another filter function has outliers. In order to actually apply these on the cluster, we need to know how to both translate the data that we have inside of our sort of Python description into bytes, and how to transform the functions that we need to apply into something serializable and applicable. So not only the functions, we actually need the total function closures. So what this means is that, or at least the way that I prefer to explain function closures, is that a function closure is a description of what you're going to do to that data and all of the context around it that you need to apply. And so this ends up becoming important because when we do serialization of functions, we need to figure out sort of automatically, we meaning Spark under the hood, needs to figure out automatically what that total function closure actually is so that it can be applied and serialized and shipped off. So how do we ship around these functions? We do something called pickling. PySpark actually uses a library called the Cloud Pickle, which was developed maybe by people who had previously worked at Berkeley. This is actually a kind of fun side note. Cloud Pickle is GPL, whereas Spark is Apache. But if you go and look at the source code, you can see that University of California, Berkeley has allowed them to use Cloud Pickle inside of Spark. So open source, working together, moving forward. So we need to be able to pickle our functions. So what really happens here, and I don't mean this for this diagram to be misleading. There's not pickling happening over the network. But pickling happens in this process. And so that's something we need to be really conscientious about when we're writing Python code, that we make sure that the code that we write is serializable. So we now have a pretty general idea of how PySpark works and how it relates to the general functioning of Spark. And I can get into being very opinionated about what I think best practices are. So first of all, REPLS and Notebooks. I like REPLS and Notebooks quite a lot. And I think that they're a really beautiful way to present information and begin to investigate. But I like to use standard tools for source control and for sharing information across an organization. And a lot of the organizations I go and I talk to actually have large teams that want to use PySpark and do somewhat complex machine learning analytic tasks. And so my recommendation is to use REPLs and notebooks for exploration and for presentation, for when you need to describe the mathematical analysis that you did and the results that you had. But when you need to be able to share functions or featureization steps across an organization, I think packaging this up ends up being very important. You need to be able to share your code. Kind of like a delicious pizza. So, what does a standard Python project look like? My awesome module has some sort of a init script in it. I can only have one module defined here, but I could have multiple. Some sort of bin directory, there's a docs directory, there's a setup.py file, which allows the Python project to be installed using sort of standard tools like easy install or pip, and tests. And this is another reason that I find it very useful, and I'm going to sort of like hammer on again in this talk, is that testing your PySpark code, both unit tests and integration tests, is much easier than debugging distributed PySpark code. So to understand how you might want to modify this standard Python project into a PySpark job or PySpark project, I think we need to think and talk about what the shape of a PySpark job is. What are sort of the repeated patterns that we see when people want to do complex machine learning or fit complex statistical models to the data that they have. So for the problems that I work on with customers, I've sort of found repeated sections that we see, and these are kind of generic sections that you see when you're doing machine learning modeling. So general PySpark structure, you parse some CLI args so that at runtime you can configure where your input files are or how many threads you're using for running local mode or so on. You're going to read in the data, so actually move from some sort of persistent data source into an RDD. You're going to turn the sort of raw data into something that's a numerical representation. So for me, that was that toSeries function. And then you're going to do fancy maths with Spark and write out data. So shout out to my colleagues in the UK for the maths. So what this translates into for me is that inside of my Python project, inside of my module, I will have a reading in the data component, which I call something like data IO, a input data to something that is a numerical representation of that, so featureization, some sort of modeling, and then more writing out. And this sort of structure, and thinking about this sort of structure, makes it easier to think about how you're going to test your PySpark code. And so keep this in mind when I get to the testing section, and I'm going to refer back to it as to why you might want to organize it this way. So a way that I know that I've written that's something that's actually testable and usable in PySpark is that my main method looks really, really simple. If you have a lot of logic in your main method, you're going to have trouble testing it, right? So here, like I said, I parse some arguments, I read in data, and then I analyze it. I have an analyze method. Not particularly descriptive, but it's at least one function that I call, but is also written somewhere else that I can go back and test. So, writing testable code. First of all, make as many functions as possible. Make as many small, simple functions as possible. This ends up being very useful for both unit testing and for when it comes to making sure that your code is actually serializable. So, like I mentioned, you need the function closures as determined by the Cloud Pickle library to be able to serialize, to be able to be serialized. And so the way that I tend to do this is to be incredibly pedantic. So I have a class, and it would be possible for me to write a function that references something else inside of that class, sort of unconsciously, because usually if you don't write a static method, the first argument in your function is going to be self. What if self has some sort of other object inside of it that isn't serializable? Well, one way to make sure that you always know what the inputs to your function are is to make your function static. So, like I said, I'm super pedantic. All of the functions that I'm going to write that I apply to my RDDs I call them static, and so if I run into a case where it isn't serializable, I know that I can look at the objects that I create inside of that function and the objects that are passed into that function, and use that to determine which one of them was not serializable in the first place. Writing testable code, for me, also means separating data input, featureization, and modeling. And so there's two types of testing that I really think you need to be able to do to make sure ahead of time that your code is pretty likely to work. You obviously need unit testing, which if you're writing many small functions that you understand, your unit test can be relatively straightforward. And if you've separated out your data I/O from your feature generation, this means that you can change your inputs at testing time. So when you go and run on a cluster, you actually use your real file that's huge and out there and distributed. And at testing time, you can use a small sample of real data, which I highly encourage doing. Usually what I'll do in my tests is I'll have a sort of resources directory that I can take a sample, use that as actual, somewhat realistic data, and run as much of my pipeline as I can over that. And then if you run into problems later on, say doing parsing of your data, if you log the records that you had trouble parsing, you can actually take those records, add them back to your sample, and make sure it runs on that locally again. So you can fix your code sort of iteratively and improve your sample testing set with real data. So writing serializable code. Like I said, keeping methods static and making sure the functions and their closures are serializable, that's generally my technique. Some things are just not serializable. Let's take a database connection. You can't serialize a database connection and ship that to another machine. I don't even think you can use it in a separate thread. So if you need to do something like you have a bunch of input records, you have some sort of ID that you can join to another data set on, and you want to be able to use some sort of database connection to do that join, then you know that you need one, but it's not serializable. And I keep repeating, you need to make your function serializable. So how are you going to do that? It's not possible to serialize it, but it's impossible-ish, meaning there are other patterns that you can use. And so this is actually a really common one that comes up, which is, I want to be able to use a database connection. How do I do that? And the short answer is that there is an operation called map partitions, which lets you sort of define a setup phase before you begin to apply whatever function you're going to apply in your map. And so that function could be a join that actually uses a database connection. And that database connection you set up at the very beginning of the function that you use inside of map partitions before you actually apply it. More testing. So whether you use Scala or Python, I highly recommend using Spark TestingBase. This was factored out of the internal Spark testing facilities. There's a GitHub URL here. And essentially, it lets you not have to worry about setting up a Spark context inside of your unit tests or integration tests. And so if you extend the Spark TestingBase class, each of your functions, when you're doing sort of like normal nose testing patterns, has a Spark context that you can get out of it and begin to develop RDDs on that. It also quiets down Py4j. So I mentioned Py4j earlier, and when run in tests, I have found that if there's an exception or a failure, you also get the full debug output of Py4j, which is incredibly not useful. The debug output for Py4j is along the lines of, I got a message C. And then the next line is, I got a message E. And if you're an internal Py4j developer, that might be useful. For me, it means nothing. And it usually clutters up all of the output logs that you got when you go back and try and understand why your test failed. So, simple example of a hello world test. So, like I said, unit test as much as possible. Integration test as much of your pipeline as you can, and if you have a really simple main method, you'll be able to integration test all of it. Things that you should test for are deviations of data from the standard format. So if there is an exception thrown when you try to parse some record, do you handle it correctly? Do you handle it well? What sort of deviations do you expect? And this is an example of why having that data I/O factored out and available to switch out your sort of like local sample is really useful, because if you have in the real world, when you actually deploy your application on the cluster, logged where that record went wrong, then you can add that back to your sample and continue on and see if you can actually make your test work. Test for RDBs with empty partitions if you want to be very meticulous. Sometimes you can run into trouble with that. And then last, but the thing that people usually want to test first, is the sort of correctness, the semantic correctness of what you intended. I strongly encourage first, emphasizing testing for unexpected inputs. If your data is big, you will have many unexpected inputs. So writing PySpark is one thing. Running it is a completely different story and takes even more knowledge of the sort of description of how Spark works and how PySpark works together with it. So writing it is easy, running it is hard. So when you go and run something on a cluster, there's two things you want to do. And here I emphasize logs, mostly so I could put the Twin Peaks log lady on a slide. But I also strongly encourage you to look at the Spark web UI. So you need to be able to know how to access and dig in to the results of what happens when you run on a cluster. I always use yarn clusters, so I have an example up here, but whatever your cluster manager is, figure out how to get at the logs. I recommend quieting down Py4j. You can do this in a log4j conf. I believe you can also do this in your code using normal Python logging facilities. And like I said, inside of your code, if there's a part where you might hit a parse exception, what I recommend doing is capturing the record that you hit the parse exception on and logging that record so you can add it back into your tests. When you look at the errors and the exceptions that you see, recognize that the first few exceptions are probably more important than the later. So in big, complex distributed systems, you can have sort of cascading failures, right? Something fails here, which causes something else to fail, which down the line causes something else to fail. And so I'll get questions from customers that have the last exception that was seen. And when I go and look at their full logs, I scroll all the way back, and it's much actually easier to identify what the initial cause was and how to actually fix that. And of course, you're going to get both the Python and the Java stack traces. And so though you may have been thinking to yourself, I will not have to learn Java, I can just use Python forever, you will definitely need to learn how to read Java stack traces and understand some of what they're saying there. And like I said, I put logs on here, but the web UI is also incredibly important. The Spark web UI allows you to see the size of your input data, the size of the shuffle, both in memory and if it's spilled to disk, how much time was spent on garbage collection. And I recommend every time you run something, go and look at it. Look at the web UI and see what the statistics look like. The reason this ends up being really useful is that you get a sense of what the numbers should look like. And so if you see something later on where like garbage collection is taking up a huge amount of time, then that might be a good indication that something is sort of wrong there. So when using Python, you really need to know the environment that you're running in. And here we're working in a distributed system. There's many computers. And so there's actually many Python installations that are getting used. There's different Python installations on each node in your cluster as well as on the driver node. So you need to think about how you manage your Python dependencies. And you need to actively manage your dependencies on your cluster. Using the default Python that's installed can really get you into trouble. If you end up wanting to change the Python version or install more libraries into the default Python, and you're using something like CentOS, then you can really bork an operating system by messing with the Python that it wants to use. And so I really recommend finding a small isolated section to put either virtualenv or Anaconda in. In older versions of Spark, it required that the driver and the worker nodes had the same Python versions. If you're working on newer versions of Spark, it's actually much easier and clearer when something like this goes wrong. So the example that I had of finding these outliers and creating pandas series, of course, required pandas to actually be installed on the cluster, as well as stats models. And so I began to sort of scratch my head and think about what's the best way to manage Python dependencies. And it's a somewhat complex topic. I've written a blog post about it, and you can find it on the Cloudera engineering blog. But the short answer is there's an environment variable that allows you to set your PySpark Python, which is the path to the Python installation that you want to use on your worker nodes. So if you go and set up a Python installation and you have all the libraries that you need inside of it, all you need to do when you run your job is make sure that that environment variable is set correctly. Thank you very much. I appreciate your attention, and I think I have some time for questions.
Question? I think we have time for maybe one or two. So.
So in general, how do you deploy your Python code to workers? Do you zip it into the X or something like this? Or maybe just copy by SSH?
I'm sorry, I couldn't hear what you said. Do you mean, was your question, how do you deploy a PySpark job, or how do you install Python libraries onto the cluster?
No, just the code. Like you have your modules in package, yeah, like featureize, etc. And now you have to deploy it to the workers, so they know about that code.
Right, so there's two ways that you can do this. If there's dependencies that you need to exist on the cluster for a large group of users, you can install it already. But if you're using Spark Submit, there's a command line flag that allows you to add either a Python file or an egg file. And so if you yourself have built some sort of complex task and it's easy to distribute as a single file or as an egg file, then you can pass it on the command line or specify it inside of your PySpark job, like on the Spark context.
Cool. One more question?
Hi. Thanks for the talk. It was very, very good, I think. Question about Python 3.4. It's officially not supported from what I actually read at least recently. Did you ever try running it with Spark and PySpark on Python 3.4? And if yes, do you have any suggestions how to take this?
I think I've only ever used Python 2.7. I believe that Python 3 is now supported in PySpark, but I have not personally run it. So if you run it, I would really love to hear how it works out for you. I am very interested in hearing.
Any more questions? Okay.
I have just a question. Have you any recommendation when you for testing Spark streaming applications?
Can you point the microphone?
Yes. Have you any recommendation for testing Spark streaming applications?
Do I have any documentation?
Recommendations
Recommendations for testing Spark?
streaming.
Oh, With Python? I have never tested Spark streaming with Python.
Okay, I believe that's the end of the time, so please join me in giving another round of applause to our speaker.